Hi, everyone. So let's go back 2 sessions and let's again look at our setting for symmetric encryption. So when we were talking about symmetric encryption, the idea was that Alice and Bob share a single key. And that's why we called it symmetric, because they both had the same secret key K. And then they used this to do encryption and decryption. So both encryption and decryption were done using the same key. And then we talked about the security properties and one-time pad. And of course, we also talked about this part, which is the key exchange, the Diffie-Hellman key exchange, which has been the main topic of the past 2 sessions. So basically here, the idea was what happens if Alice and Bob don't share a key at the beginning? How can we make sure that they share something in the end? And this was the simple idea in Diffie-Hellman. Again, we said that we choose some prime number P and some primitive root G. Then Alice chooses a secret A, Bob chooses a secret B. And then instead of sending A, Alice just sends G to the power of A. And instead of sending B, Bob sends G to the power of B. And then both sides can compute G to the power of AB. Bob can do this by taking G to the power of A, which was sent to him by Alice, and raising it to the power of B, which was his own secret. And Alice can compute the same value by taking G to the power of B, which was sent to her by Bob, and then raising it to the power of A, which was her own secret. Okay. Now, today we want to talk about something a little bit different, and this is what we call asymmetric cryptography or public key cryptography. Or let's say asymmetric encryption. And the idea here is quite simple. The idea is that I want the key that I use for encryption to be different from the key that I use for decryption. Okay, so I'm going to have two different keys now. And there is going to be an encryption key, and this encryption key is going to be public. So imagine that Alice creates an encryption key. She just publishes it to everyone. So anyone who wants to send a message to Alice can just use Alice's encryption key, right? But then there is also a decryption key, which is private to Alice, and only Alice knows about it. Okay, and that's what you need to do the decryption. So this is my setting. There are two keys. We're going to have a public key, or we sometimes also call it encryption key. And I'm writing this one in blue because everyone knows it. And then we're also going to have a private key or a decryption key. And the idea is that only one person knows this one. Let's give them some name. Let's say this is, well, public and private, or encryption and decryption. So I'm going to call this one K sub E, and I'm going to call this one K sub D. So the encryption key and the decryption key. Okay. Now, again, just like before, we have to say what are the properties that I would like to have. See, I have to go back here. You know, we had a definition here which basically said if I encrypt something and then I decrypt it, I should get the original message back. So of course I want the same thing. And then we had these security properties. I want them as well. The only difference is that I want to use different keys for the encryption and decryption. Okay. So what I'm going to say here is that there are two algorithms. And remember, our algorithms are always public. Everyone knows the algorithms. So there are two algorithms, or maybe you can also think of them as functions. So we have encryption, which takes a string and gives us another string. And this encryption is done using the key for encryption. So it's done using the public key. And we also have a decryption algorithm. This one also maps strings to strings. So it takes encrypted strings and decrypts them. But this one should be using the private key or the decryption key. And of course, the property that I want to have is pretty much the same as before. I want to say that for any message M, if I first encrypt M, and of course, I'm doing the encryption using the public key, and then I decrypt the result. And again, of course, I'm doing the decryption using the private key. I should get the same message M back. Okay. Now, the really important point here is that the public key, as the name suggests, is public, and the private key is private. So the idea here is that, let's say you're Alice, you want to receive messages from many different people. You just create this key pair, you create a public key and a private key, and then you publish the public key. So everyone knows the public key, but only you know the private key. So everyone on the internet, let's say, can send you encrypted messages. They can run this encryption, encrypt a message, send it to you, but then only you can decrypt it. Okay. And of course, I want to have the same security properties as before. Okay. So I'm not going to write the security properties here. You know, that's like, we're not changing it from the symmetric case. So basically, if I have an eavesdropper, the eavesdropper should not be able to find out anything about my messages. So this is the situation. Let's say, actually, let me do it in red. So let's say this is Alice. She has a private key, KD, or a decryption key, and she just publishes the public key to everyone. So this is just sending the public key over to everyone. And of course, as usual, I have Eve, who can see all of this. Okay, in color, let's say. This is Eve, and Eve sees everything. But at this point, it's not important because anyway, Alice is publishing this to everyone. So even Eve can send messages to Alice if she wants to. And then on the other hand, I can have many different people. So let's say I have Bob, maybe Carol and Dave. Now, if they want to send messages to Alice, let's say Bob wants to send M1, Carol wants to send M2, Dave wants to send M3. They all know this public key KE because it's public. And sorry, these messages, I have to write them in red because the messages are private. So the way Bob sends M1 is that he just encrypts it using the public key of Alice. So he sends encryption using this public key of M1. And Carol does the same thing for M2. So encryption using the public key of M2. And of course, Dave does the same thing with M3. Encryption using the public key of M3. And Eve sees all of these encrypted messages, but our security property says that even if she sees a lot of these encrypted messages, she shouldn't be able to get any information. And then, of course, only Alice can decrypt these messages because Alice can just use the decryption function using the decryption key to get M1, M2, and M3. So Alice ends up knowing M1, M2, and M3, but no one else knows. Now, the question is, of course, how do I design such a system? What should be my private key? What should be my public key? What should be my encryption and decryption functions? And the first system we're going to see is actually called the ElGamal system. For those of you who speak Arabic, this is how it's written. And yeah, so we're going to take the same idea that we had for Diffie-Hellman key exchange, and we're going to make it non-interactive. So let me just copy the Diffie-Hellman key exchange. Look, here the secret was G to the power of AB, right? And then we said that later on, we would use this G to the power of AB in a one-time path. So imagine that Bob wanted to send some message M to Alice. So Bob also knows a secret M. Now, previously, they would just do a key exchange. So they would choose a P and a G. And actually, in this case, let's say that Alice chooses it. So Alice sends P and G to Bob. And then Alice also sent G to the power of A, where A was Alice's secret. Bob sent G to the power of B, where B was Bob's secret. And then both sides could just compute G to the power of AB. And when they compute G to the power of AB, now they have a shared secret. Now, suppose that Bob wants to send the message M to Alice. Instead of sending M itself, Bob can just send M plus G to the power of AB. Right? And of course, again, everything is modulo P. All of our messages, all of our computations are modulo that big prime number P that we always have. Okay. Now, the thing here is that, of course, this doesn't really satisfy our system. It's not really an encryption and decryption function because this is interactive. Alice should send messages to Bob, then Bob should send messages to Alice, and so on. Right? But specifically, I also changed this so that Alice is the one who chooses P and G. So now if you look at this system, you see that all the messages that are sent from Alice to Bob are before all the messages that are sent from Bob to Alice, right? So instead of sending these messages to Bob, Alice can just broadcast these messages. She can just publish these values, let's say, on her website, and then anyone can see these values, and anyone can use these values to send messages to Alice, right? So there is nothing special about Bob here. Like, instead of Bob, I can have anyone else. And also, I want you to realize that Alice here can actually decrypt the message. Because Alice can compute G to the power of AB, this is just like in Diffie-Hellman. But when she calculates G to the power of AB, and when she sees this message, she can easily decrypt this message, right? So she just takes whatever this message is, let's call this M prime, and then she just calculates M, which is going to be M prime minus G to the power of AB, right? She knows M prime because M prime is the encrypted message that Bob sent her. And she knows G to the power of AB because that's the shared secret that we had before. Okay? So now let's just formalize this. So these are our steps. In step 1, Alice chooses a big prime number, just like before. Right, let's call this big prime number P. And she also chooses a G. So she chooses a primitive root G. And additionally, she also chooses a secret value A. Okay. And remember that all of my numbers R modulo P. And a secret A, but this A is also, let's say, between 1 to P minus 1. And what does she publish? So she publishes these things. She basically publishes P, she publishes G, and she publishes G to the power of A mod P. Right? These are all the messages that are being sent here. But again, I'm not sending these messages to Bob. At this point, there is no Bob. Alice is just broadcasting these messages to everyone. Okay? Nice. And then in the next step, in step 2, let's say that Bob wants to send a message to Alice. So Bob has a secret message. Let's call this M, that he wants to send to Alice. Now, what does Bob do? We said that Bob first chooses a random secret B, and then he computes G to the power of AB. And then adds this G to the power of AB to his message and sends that to Alice. Okay? So this is what's going to happen. Bob chooses some random number B, which is going to be a secret, again, between 1 to P minus 1. And now, what should he send to Alice? Well, he has to send G to the power of B. So we send G to the power of B, and remember, everything is always mod P. And we should also send M prime, which is our original message, plus G to the power of AB. So my original message plus G to the power of AB mod P. And again, just as in Diffie-Hellman, Bob can compute G to the power of AB because G to the power of A was public. Everyone knows G to the power of A. Alice made that public. And Bob knows B, so he can just raise G to the power of A to the power of B, and he can get G to the power of AB. Okay. Now, the third step is, of course, Alice decrypting it. But I just want to go back here, and I want to talk about what every aspect here is. So look, we said we're going to have a public key and a private key. So what is the public key here? Maybe tell me in the chat. What is my public key in this system? So my public key consists of all the things that Alice is making public in the beginning. So all of this is my public key. Okay. So this is my public key. Now, this might seem a little bit weird because we're used to the idea that the keys should be just one number. But again, remember that whenever I talk about anything, whenever I talk about a key, a message, a random number, whatever, all of these are basically strings. And in a string, I can encode several numbers, right? And here I want to encode 3 different numbers. I want to encode P, G, and G to the power of A modulo P. And this triple is my public key. Okay. Now, why is this the public key? Because anyone who knows this can send an encrypted message to Alice. Okay. Now, what is the private key? The private key, we said, is the secret that Alice should know in order to encrypt the messages. what is the secret that only Alice knows? It's A. So actually, my private key or my decryption key is just A. Now, this might, again, seem a little bit weird that my public key is much longer and has much more information in it than my private key, but that's fine because the only thing that I needed here was that the public key should be public and people should be able to do encryption using the public key. The private key should be known only to Alice, and she should be able to do decryption using the private key. And as we'll see, we have all of these properties. Okay. Now, what is this message that Bob is sending to Alice? This message is the encryption of M, right? So this is my encryption function. So encryption of M using the public key KE is going to be this whole thing. Now, of course, it's important that Bob can compute this, and we've already shown that you can compute this. So if you know KE, which means that you know the prime number P, you know the primitive root G, and you know G to the power of A. And if you also know the message M, of course, you can compute all of these things. So you have your random number B, so you can compute G to the power of B. That's the first part of the encryption. You also can compute G to the power of AB because you know G to the power of A and you know B, so you just raise G to the power of A to the power of B. And when you know G to the power of AB, you can just add that to M, and you get M prime, which is M plus G to the power of AB. And so you can compute all the parts of this encryption. Now, the thing that I want you to realize here is that my encryption is not unique, right? So this is not really just a function. It's not a deterministic function, let's say, because I'm choosing a random number B. So the same message M can have many different encryptions based on what the B was. But that's fine. We're okay with that, as long as we satisfy this property. So it's not just mapping strings to strings. It's non-deterministic, okay? But as long as I say that any result of the encryption can be decrypted and give me the same message, I'm happy with that. Okay. Now, finally, Alice should decrypt Bob's message. So we say Alice decrypts Bob's message. And basically, when she decrypts, she's going to decrypt using her private key, using her decryption key, which was A. So this is a decryption using A of the encrypted message. And the encrypted message, I'm not going to write the mod piece again. It just had G to the power of B and M plus G to the power of AB. So this is the decryption of G to the power of B and M plus G to the power of AB. And I'm saying that this decryption should give me M. So basically, what I'm saying here is that you should have an algorithm, a decryption algorithm, that if you know A, G to the power of B, and M plus G to the power of AB, it gives you M. But of course I have that, right? Because if I have G to the power of B, I raise it to the power of A, that gives me G to the power of AB. But I have M plus G to the power of AB, so I just subtract G to the power of AB, and that gives me M. Okay? So this is what we call the ElGamal crypto system. And this is an asymmetric encryption system because, as we saw here, basically Alice can create an encryption key or a public key, and she can publicize this to everyone. So she's sending this P, G, and G to the power of A, not just to Bob, but just to everyone. And actually, so maybe let me change this figure a little bit. So instead of sending it to Bob, let's say this is just public. So everyone can see this. Now, again, just like before, suppose that I have several different people who want to send messages to Alice. I have Bob, Carol, and Dave. They each have their own message. They can each choose a secret B for themselves, and this secret is going to be different because they're choosing this randomly. And then they can use this encryption, which is basically all the messages that Bob was sending here, right? And then only Alice can decrypt. Basically, Alice will have a shared value, G to the power of AB, with each of these people. And the shared value that Alice will have with Bob is different than the shared value that she has with Carol and the shared value that she has with Dave. So it's not like Bob or Carol can read Dave's messages, only Alice can decrypt. Okay, nice. So these are all the nice properties that I wanted. But of course, the only thing here is that my encryption is now probabilistic. So I can take the same message and I can have many different encryptions. But that's fine. I mean, it's not a big deal because, well, as long as I can decrypt it and as long as I have the security properties, who cares if a message has many different encryptions? Nice. So this is the ElGamal system. It's basically the same as Diffie-Hellman, except that it's no longer interactive in the sense that Alice can just publicize the public key. She can just publish all of these values, and then she can go offline. So again, imagine the case of an email server. Alice has published these, let's say, on her website. You can use it to send encrypted email to Alice, and Alice is offline. Then Bob comes along and he sends an encrypted email to Alice. So the email server just knows these encrypted messages. So the email server just knows these, right? So the email service provider cannot decrypt this, but when Alice comes online, she sees this encrypted message and she can decrypt it and she can read the original message. So you see the huge difference here between ElGamal and Diffie-Hellman is that in Diffie-Hellman, we had to have both sides online to send messages back and forth. But here, one side just publishes the key and goes offline, and then she can receive messages from many different people. And when she comes back online, she can read all of those messages. Okay. So this is ElGamal. The other system that I want to show you is called RSA. Now, RSA is a little bit different in the sense that we have a different encryption key and a different decryption key, but a lot of things are actually quite similar. Now, let me do RSA. Actually, let me make sure you can see the screen correctly. I don't know what's going on with the screen share. For some reason, I cannot control the screen share. I don't know what's happening. Okay. Let's hope this works. Can you tell me in the chat if you can see my screen? Can you see this? Yes, okay. So the error I was getting was for nothing then. Okay, so we also can talk about RSA encryption. And RSA is also named after the people who invented it. So it's Rivest Adelman and Shamir. Now, the idea in RSA is a little bit different, and it needs a little bit more number theory. But one nice difference is that your encryption would be unique. So if I give you a particular message, you will only have a unique encryption. So here's the idea. Let's say that I have some number n, and I want to do all of my calculations modulo n now, okay? Now, previously, my modulus was a prime number, but now this n is not necessarily a prime number. Actually, we will see that it's never a prime number. But just as before, I'm just choosing a modulus. And just imagine that this modulus is big enough that I can basically represent all of the messages that I want to send as numbers between 1 and n-1, or between 0 and n-1. Okay. Now, I want to have a very simple encryption and decryption mechanism. So I want to have the two keys. And actually, instead of writing KE and KD, I'm just going to write E and D because that's easier, right? So I'm going to have a public key or encryption key E. And again, this E is going to be a number modulo n. So between 1, 2 to n-1, let's say. And I'm going to also have a private key or a decryption key. I'm going to call this one D. And this is also going to be a number modulo n. Okay. Great. Now, I want my encryption and decryption to be super simple. So here's what I want to say. I want to say when I encrypt a number using the public key E, so when I encrypt some message using this key E, I want the result to just be the message raised to the power of E. Okay. And of course, again, all of my calculations are modulo n. So that's my encryption. I want to have a very simple encryption. Whenever I want to encrypt a message M with the encryption key E, all I do is that I take M and I raise it to the power of E. And similarly, I want my decryption to also be very simple. So if I'm decrypting using the key D, some encrypted message, let's call this one M prime. Okay, I just want to get M prime to the power of D modulo n. So I want basically to have the same encryption and decryption functions. It's just that I'm using different keys. Both my encryption and my decryption is just to take the message and raise it to the power of the key. The only difference is that the encryption does this with the encryption key, with the public key, and the decryption does it with the decryption or secret key. Okay? Now, of course, I need to choose my encryption and decryption key in a smart way. I have to, first of all, make sure that they make sense, in the sense that if I encrypt something and then decrypt it, I get the same thing back, right? So this is the property that we should always have. I should make sure that for every message M, if I first encrypt M using my encryption key, and then I decrypt the result using my decryption key, I should get M back, right? And of course, this is for every M that is a number modulo n. Again, I don't have enough space to write it, but I'm thinking of all of my messages as being numbers modulo this n. Okay, so I definitely should choose E and D to make sure I have this property, because otherwise, what's the point if I cannot decrypt what I encrypt? And then, of course, I also need the security properties. And the security property here is that if someone doesn't know D, they shouldn't be able to find the message M, or they shouldn't be able to find information about M. So let's say I write it here. So let's say Eve sees the encryption of M. So that's encryption using E of the message M, which is just M to the power of E. And let's say that my modulus is also known to everyone. So Eve knows the modulus N. Okay, so she sees M to the power of E and also knows my modulus N, but she does not know the decryption key or the secret key D. Okay. In this case, Eve should not be able to basically do the decryption and find the M. So Eve cannot find M. Again, as before, this is the weak property. The strong property would be that she shouldn't find much information about M. She shouldn't be able to narrow M down to a small set, let's say. Okay. How do we make this work? Now, this is extremely clever. So let me just go here and start with this first property. So what is the encryption of M? Encryption of M is just M to the power of E. And what is the decryption of this M to the power of E? It would be M to the power of E to the power of D. So it's just M to the power of E times D. And this should be equal to M, right? So, and I should have this for every M. I'm just rewriting the requirement that when I encrypt a message and I decrypt it, I get the same message. And what that means is that for every M, I should have M to the power of ED is equal to M, based on my definition of encryption and decryption. So I have to somehow create my keys, E and D, to ensure this, to ensure that if I take any number and I raise it to the power of E times D, I get that number back. Now, we had something similar to this when we were talking about Fermat's little theorem. Remember, we had this idea that if our modulus is a prime number, I can raise any number to the power of P, and that would be equal to that same number modulo P. But my modulus is not a prime number here, and we will soon see why it's not a prime. Okay, so let's see what happens if I actually want my modulus to be a prime number. So this is my first attempt, and this is not going to work. Okay, so maybe here, instead of saying that this is RSA, let me just say this is the intuition behind RSA. And then let's do our first attempt, which is going to fail. My first attempt is going to be this. I'm going to say let my N, my modulus, be a prime number. Because I use the prime number for Diffie-Hellman, and I also use the prime number for ElGamal, so why not here? Let's see what happens if P is a prime number. So I want this. I want for every M to have M to the power of ED equals M. Okay. So I want to somehow choose my keys. I want to somehow choose my decryption key and my encryption key such that for every m, I have m to the power of ed equals m modulo p. Okay. But now, what does this mean? This means that, and let's say my m is never 0. I'm never sending 0. So this m is between, okay, let me write it more formally. Let's say for every m that is from 1 to p minus 1, I want m to the power of ed to be equal to m modulo p, right? Okay. Now, what does this mean? Let's just divide both sides by m. And by the way, I can divide by m because m is not 0. So m is actually co-prime to p, and I have an inverse. Okay. We will have a session on number theory where we will talk about modular multiplicative inverse. So I'm just going to write it here. You can search on Wikipedia for this as well. We will actually have a tutorial session in which we will go over this. But basically, the idea is that I have division when I'm doing my calculations modulo a prime number p. So I can divide by m. So I'm saying that for every m between 1 and p minus 1, I have m to the power of ed minus 1 is equal to 1 modulo p. Okay. But now here's the thing. We can use Fermat's little theorem here. From Fermat's little theorem, what do I know there? I know that for every m to the power of p minus 1 is equal to 1 mod p. And again, this is for every m that is not 0 modulo p. Okay. Now, and here maybe I should also write for every m that is not 0. So here's the idea. If I choose this power here, ed minus 1, to be a multiple of p minus 1, I can be sure that m to the power of ed minus 1 is always going to be 1. Okay, so that's my idea. Make sure that p minus 1 is a divisor of ed minus 1. Or in other words, make sure that ed minus 1 is some number, let's call it k, times p minus 1. Okay? If I have this, then my problem is solved. Then I can say that m to the power of ed minus 1 is just m to the power of p minus 1, all of it to the power of k, but m to the power of p minus 1 was 1, and 1 to the power of k is going to be 1. So m to the power of ed minus 1 is going to be 1, which means that if I multiply both sides by m to the power of ed is going to be equal to m. Right? Which is exactly what I wanted, because this is encrypting and then decrypting m. But now the problem is, how do I choose my E and D? Okay. So here's what I need. I need ED minus 1 to be a multiple of P minus 1, right? So if I do my calculations modulo P minus 1, it means that ED minus 1 is equal to 0 modulo P minus 1, which means that ED is equal to 1 modulo P minus 1. But unfortunately, this means that D is just the inverse of E modulo P minus 1. And inverses are easy to compute. again, we will have a session about computing inverses. But basically what this means is that my private key D can easily be computed from my public key E. Remember, what was I doing here? I was saying that I make E public to everyone. Everyone is going to know the public key or the encryption key. But this private key or decryption key was supposed to be private. This is something that only Alice knows. But if I choose my modulus to be a prime number, I get into this problem where basically anyone who knows E can also compute D. Because D is just the inverse of E modulo P minus 1. And everyone knows P, so everyone knows P minus 1. Everyone knows E, so everyone knows the inverse of E. So the reason we don't use a prime modulus, and this attempt is going to fail, is that if I use a prime modulus, then anyone who knows my public key E is going to also be able to compute my secret key D. And of course, that's terrible. I don't want that. So in the next session, we're going to see how to choose this number N so that we don't have these kinds of problems. And we're also going to see how to compute these inverses. Okay, so that's it for now. I'll see you next week.